Before we learn the definition of continuity, let us see the graphs of few functions. Let us consider the function f of x, and it is defined as 1 if x is less than or equal to 0 and 2 if x is greater than 0. For x less than or equal to 0, f of x is a constant function 1, and for x greater than 0, it is a constant function 2. For x is equal to 1, f of x is 1. That's why for x is equal to 0 at 2, there is a bubble. When we try to draw the graph of this function, we cannot draw it in one stroke. That is, without lifting the pen from the paper, we cannot draw, because there is a jump in the graph, or there is a gap in the graph at x is equal to 0. So, we say that the function is discontinuous at x is equal to 0. Now, consider this function f of x is equal to 1 when x is not equal to 0 and 2 when x is equal to 0. Let us draw the graph of this function. If x is equal to 0, f of x is 2, and for all other real values, f of x is 1. At 0, 1, we have a bubble, because at x is equal to 0, y is 2. In this graph, there is a hole at x is equal to 0. Therefore, we say that the function f of x is discontinuous at x is equal to 0. Now, let us consider a third function, f of x is equal to 1 divided by x, reciprocal function. Here x cannot take the value 0. This is the graph of f of x is equal to 1 by x function, and as x approaches 0 from the right side of 0, it takes the value infinity, and as x approaches 0 from the left side of 0, f of x takes the value minus infinity. Here y-axis is called an asymptote to this curve. An asymptote of a curve is a line which is a tangent to the curve at a point at infinity. That is, it goes closer and closer to the curve, but it won't touch the curve. Here also the function is discontinuous at x is equal to 0. Therefore, a function f of x is said to be discontinuous if it has a hole or a jump or an asymptote in its domain. All these three functions are discontinuous at x is equal to 0. Therefore, if the graph of f of x has no holes or gaps or asymptotes at a point x is equal to c, then we say that f of x is continuous at x is equal to c. So, for the function f of x to be continuous at x is equal to c, the first condition is f of c should be defined, that is, without any hole or gap at c. And the second condition is limit extending to c of f of x should exist. And the third condition is these two must be equal. Limit extending to c of f of x must be equal to f of c. We can write this limit as limit extending to c minus f of x, which is LHL, limit extending to c plus f of x, which is RHL. We say that the limit exists only when LHL is equal to RHL, and these two must be equal to f of c. Then we say that f is continuous at x is equal to c. Here we are checking the continuity only at one point x is equal to c, and a real function f is said to be continuous if it is continuous at every point in the domain of f. Let us consider the function f of x, which is a polynomial a0, a1x plus etc. plus an x raised to n, where n is a natural number, an is not equal to 0, and ai's are real numbers. In a polynomial, the powers of x will be positive integers. No negative powers and no fractional powers are allowed. And if c is any real number, then limit extending to c of f of x can be calculated easily, which is f of c. Therefore, we conclude that every polynomial is continuous. Similarly, we can see that exponential function, logarithmic function, sine function, cos function are also continuous functions. Now we will discuss the continuity of absolute value of x, and we know the definition of absolute value of x. It becomes x for x greater than or equal to 0 and minus x for x less than 0. For x greater than or equal to 0, it is an identity function. It is y equal to x, where y is f of x, and for negative values it is minus x. As we approach 0 from the right hand side or from the left hand side, f of x tends to the same value 0. So there is no jump or there is no hole in the graph. So it is a continuous function. We will first check the continuity at x is equal to 0. So LHL at 0 will be limit x tending to 0 minus f of x. For less than 0, f of x is minus x. The answer is 0. Now RHL, limit x tending to 0 plus f of x, and for 0 plus, that is greater than 0 definition, which is x, and the limit value is 0, and f of 0 is absolute value of 0, that is also 0. All three are equal. LHL equal to RHL equal to f of 0. Therefore, f of x is continuous at x is equal to 0. Now let us discuss for the other real values. We will take c in the interval minus infinity to 0. We checked the continuity at 0. Now we will check the continuity for all real values in the interval minus infinity to 0. Limit x tending to c of f of x. In this interval, c values are all negative. Therefore, f of x is minus x, and the answer is minus c. And f of c, c being negative, again the answer is minus c. Therefore, f is continuous in the interval minus infinity to 0. In the figure also, for negative values of x, we have a ray y equal to minus x, which is continuous. Now the third case, we will take c value in the next interval, 0 to infinity. Any real value in the interval 0 to infinity. Limit x tending to c of f of x. Here c values are all positive. For positive real values, f of x is x. The answer is c. And f of c, c is positive. We have to use the definition x. Therefore, f of c is c. Both are equal. Therefore, f is continuous in the interval 0 to infinity. In the graph for x greater than or equal to 0, we have a ray y equal to x, which is continuous. Therefore, we can conclude that f is continuous in R. From the graph itself, we can make out there is no gap or jump in the graph. Therefore, absolute value function is a continuous function. Now, let us discuss the continuity of the Signum function, which is absolute value of x over x when x is not equal to 0 and 0 when x is equal to 0. The Signum function can be defined as 1 when x is greater than 0, 0 when x is equal to 0 and minus 1 when x is less than 0. If x is positive, absolute value of x becomes plus x. Therefore, the Signum function takes the value 1. And if x is less than 0, absolute value of x becomes minus x. Therefore, it takes the value minus 1. And if we see the graph of this function, for x is equal to 0, the answer is 0. For x greater than 0, it takes a constant function 1. And for x less than 0, it takes a constant function minus 1. If you see, we have gaps in this function at x is equal to 0. Therefore, it is discontinuous at x is equal to 0. For other real values, it is continuous. There is no gap at other values of x. Now, let us write the proof for this. We will first check at x is equal to 0. LHL will be limit extending to 0 minus of f of x. For less than 0, f of x is minus 1. And the answer is minus 1. RHL is equal to limit extending to 0 plus f of x, which is limit extending to 0 plus. For x greater than 0, f of x is 1, which is a constant. Therefore, limit value is 1. And here LHL is not equal to RHL. Therefore, f is discontinuous at x is equal to 0. Now, we have to check for the other real values. Now, case 2, we will check for all negative real numbers. For all negative real values, we have only one definition, which is minus 1. So, we need not do LHL, RHL. We will combine both as limit extending to c of f of x, and c is negative. For negative values, f of x is minus 1. Therefore, the answer is minus 1. And f of c is negative. Therefore, the answer is minus 1. Both are equal. Therefore, f is continuous in the interval minus infinity to 0. Similarly, let us do case 3. We will check for all real values in the interval 0 to infinity, positive real values. We have only one definition for positive values, so we need not do LHL, RHL. Limit extending to c of f of x is limit extending to c of, for positive real values, f of x is 1. The answer is 1. And f of c is positive. Therefore, the definition is 1. Both are equal. Therefore, f is continuous in the interval 0 to infinity. So, we have only one point of discontinuity, which is x is equal to 0. Therefore, the signum function f of x is continuous in R minus 0, or we may say that it is discontinuous at x is equal to 0. Now, let us discuss the continuity of greatest integer function. We know that for all real values in the interval 0 to 1, including 0, f of x becomes 0. And for all real values between 1 and 2, including 1, f of x becomes 1. We will draw the graph of this function. F of 0 is 0, and for all real values between 0 and 1, f of x is 0. And for 1, the answer is 1. Greatest integer function of 1 is 1. And for all real values between 1 and 2, the answer is 1. For 2, the answer is 2. And see the graph, we have gap at every integer. So, at every integer, the function is discontinuous. And for other real values, we don't have any problem. For example, if we take 1.5, there is no gap in the graph. The function is continuous at x is equal to 1.5. Only at integral values, the function is discontinuous. Case 1, we will take c belonging to z. C can take any integral value. We need to do LHL and RHL. Let us consider the integer 1. As we approach 1 from the left hand side, we have to take a very close real value. Let us take 0.99. The greatest integer function of 0.99 becomes 0. As we approach 1 from the left side of 1, the function f of x takes the value 0. Similarly, as we approach 1 from the right side of 1, let us consider a very close real value, 1.001. The greatest integer function of 1.001 becomes 1. So, LHL and RHL are not the same. Therefore, we have to do LHL and RHL for the greatest integer function at all integral values. LHL is equal to limit extending to c minus of f of x, and f of x is the greatest integer function. As x approaches c, where c is an integer, let us take a very close left hand side value of c. The greatest integer function will become c minus 1. For example, if we consider the integer 2, let us take a very close value on the left side of 2. Let us take 1.9. The greatest integer function of 1.9 becomes 1. Therefore, limit extending to c minus of greatest integer function becomes c minus 1. RHL is equal to limit extending to c plus f of x, which is limit extending to c plus greatest integer function of x is equal to, as we approach c from the right side of c. For example, let us consider the integer 2, and we will take a very close value on the right side of 2, 2.001. The greatest integer function of 2.001 becomes 2. Therefore, as x tends to c plus, the greatest integer function of x becomes c. And these two values are not the same. LHL not equal to RHL. Therefore, f of x, which is the greatest integer function, is discontinuous at all integers. Now, case 2, we will check at non-integral values. So, we will take c as any real value other than integers r minus z. For example, let us consider a non-integral value 1.5. The greatest integer function of 1.5 becomes 1. Whether we approach 1.5 from the left hand side or from the right hand side, the answer is going to be 1. Therefore, we need not do LHL and RHL in this case. Limit extending to c, where c is a non-integral value of f of x, is limit extending to c of greatest integer function of x, which becomes greatest integer function of c. That is greatest integer function of 1.5. Whatever value we are taking for c, greatest integer function of that we will get. And f of c is also the same value. Both are equal. Therefore, f of x is continuous for all c belonging to r minus z. Therefore, we conclude that f of x is discontinuous at all integers. For non-integers, it is a continuous function. Now, let us see properties of continuous functions. Suppose f and g be two real functions continuous at a real number c, then f plus g is continuous at x is equal to c, f minus g is continuous at c, f into g is continuous at c, f divided by g is continuous at c, provided g of c is not equal to 0. Using this property, we can conclude that f of x divided by g of x, where g of x is not equal to 0, that is, this is a rational function, is continuous. Because f of x and g of x are polynomials, and we know that polynomial functions are continuous everywhere. Therefore, every rational function is continuous in its domain, that is, where g of x is not equal to 0. Theorem 2. Suppose f and g are real valued functions such that f composite g is defined at C. If g is continuous at C and if f is continuous at g of C, then f composite g is continuous at C. We will learn this theorem without the proof. So, composition of two functions is also continuous at that point. There are few techniques for evaluating the limit questions under different conditions, and it is important to know when to apply which technique. If we come across limit extending to c of f of x, we directly substitute c. If we get a constant, the limit exists and the limit value is that constant. If we have limit extending to c of f of x, by substituting x is equal to c in the function, if we get constant by 0, we conclude that the limit does not exist. Probably it is an asymptote, which is the point of discontinuity. And by substituting x is equal to c, if we get 0 by 0 form, that means there is a hole or gap in the graph. In such cases, we use one of the following four methods. We use factorization if it is a rational function, or we can use rationalization, substitution, or formula. When we apply the limits and if we get 0 by 0 form, we use one of the four methods according to the question, and then we apply the limits. Now we will write list of limit formulae which we learnt in 11th standard. First one, limit extending to 0 of sin x divided by x is 1. Limit extending to 0 of 1 minus cos x divided by x is 0. And remember, this formula can be applied only in the numerator, not in the denominator. Limit extending to a of x raised to n minus a raised to n divided by x minus a is equal to n into a raised to n minus 1. Limit extending to 0 of e raised to x minus 1 divided by x is 1. Limit extending to 0 of log of 1 plus x divided by x is 1. Exercise 5.1. Question number 1. Prove that the function f of x equal to 5x minus 3 is continuous at x is equal to 0, at x is equal to minus 3 and at x is equal to 5. We will first check at x is equal to 0. F of x is a polynomial. For polynomials, we need not do LHL and RHL. Even if you do, the answers will be the same. So, we will combine LHL and RHL and write it as limit extending to 0. That means 0 plus and 0 minus both are included in this. Is limit extending to 0 of 5x minus 3. The function is defined at 0, so we can directly substitute the limit value. We get 0 minus 3. The answer is minus 3. And f of 0, substituting 0 in f of x, we get 0 minus 3. That is also minus 3. Limit extending to 0 of f of x and f of 0 are equal. Therefore, f is continuous at x equal to 0. Now, we will check at x is equal to minus 3. Limit extending to minus 3 of f of x is equal to limit extending to minus 3 of 5x minus 3. We can directly substitute minus 3 minus 15 minus 3 is minus 18, and f of minus 3, substituting minus 3 in the given expression, we get minus 15 minus 3, that is also minus 18. Limit extending to minus 3 of f of x and f of minus 3 are equal. Therefore, f is continuous at x equal to minus 3. Now let us check at x is equal to 5. Limit extending to 5 of f of x is equal to limit extending to 5 of 5x minus 3. Substituting the limit value, we get 25 minus 3, which is 22. And f of 5, substituting 5 in the given expression, we get 25 minus 3, which is 22. Limit extending to 5 of f of x equal to f of 5. Therefore, f is continuous at x equal to 5. Second question, examine the continuity of the function f of x equal to 2x square minus 1 at x is equal to 3. In this question also f of x is a polynomial. We need not do LHL and RHL. We will calculate limit extending to 3 of f of x, that is limit extending to 3 of 2x square minus 1. We will directly substitute the limit value because the function is defined at 3. 2 9s are 18 minus 1, which is 17. And f of 3 is equal to 2 times 3 square. 2 9s are 18 minus 1, which is 17. Limit extending to 3 of f of x and f of 3 are equal. Therefore, f is continuous at x equal to 3. Question number 3. Examine the following functions for continuity. First subdivision, A, f of x is x minus 5. And in this question, it is not mentioned at which point we have to check the continuity. And the given function is a polynomial. Therefore, we will check for all real values. Let c belongs to R. Limit extending to any real value c of f of x is equal to limit extending to c of x minus 5. Polynomials are defined for all real values. We can directly substitute the limit value. We get c minus 5, and f of c is also c minus 5. Limit extending to c of f of x is equal to f of c. Therefore, f is continuous at c, where c belongs to R. That means f of x is continuous at every real number. Therefore, f is a continuous function. Second subdivision, f of x is 1 divided by x minus 5, where x is not equal to 5. This is a reciprocal function. Here we will take c belonging to R minus 5 because in its domain we don't have 5. Limit extending to c of f of x equal to limit extending to c of 1 over x minus 5. Here c doesn't take the value 5, so we can directly substitute x as c. The answer is 1 divided by c minus 5, and f of c is also 1 divided by c minus 5. Therefore, limit extending to c of f of x is equal to f of c. Therefore, f is continuous in R minus 5, that is, f is continuous in its domain. C subdivision, f of x is given as x square minus 25 over x plus 5, where x is not equal to minus 5. We will take c as any real value other than minus 5. because at minus 5 the function is not defined. Limit extending to c of f of x is equal to limit extending to c of the given rational expression. Limit extending to c of, we can factorize the numerator x minus 5 times x plus 5 over x plus 5. These two factors are getting cancelled. Now by applying the limit value we get c minus 5, and f of c is c square minus 25 over c plus 5, which can be simplified further by doing factorization of the numerator. This answer is also c minus 5. Limit extending to c of f of x and f of c are equal. Therefore, f is a continuous function in its domain. D subdivision, f of x is equal to absolute value of x minus 5. We know the definition of absolute value of x. It is x for x greater than or equal to 0 and minus x for x less than 0. Similarly, the definition for absolute value of x minus 5 will be x minus 5 when x is greater than or equal to 5. Because if x value is greater than or equal to 5, x minus 5 will be greater than or equal to 0. So, absolute value sign can be removed. And for x less than 5, it will be minus of x minus 5. Because for lesser than 5 values, x minus 5 will be negative. To make it positive, we have to put a negative sign. First, we will check the continuity at 5. And then we will check for all real values less than 5 and then for all real values more than 5. Case 1, at x equal to 5. We have to do LHL and RHL at x is equal to 5. LHL will be limit extending to 5 minus f of x, which is limit extending to 5 minus. For 5 minus, we need to use x less than 5 definition, which is minus of x minus 5, and it is a polynomial. We will directly substitute the limit value. 5 minus means we are approaching 5 from the left hand side of 5. It is not minus 5. Therefore, by substituting x as 5, we get 5 minus 5, 0. RHL is limit extending to 5 plus f of x, which is limit extending to 5 plus. For 5 plus, we will use greater than or equal to 5 definition, which is x minus 5. Substituting the limit value, we get 5 minus 5, which is 0. And f of 5 equal to 5 definition, which is x minus 5. 5 minus 5, this is also 0. LHL equal to RHL equal to f of 5. Therefore, f is continuous at x equal to 5. Case 2. Now, we will check for all real values which are less than 5. Let c be a real value belonging to the interval minus infinity to 5. Open at 5 because already we have checked at 5. For all these values, we have only one definition, less than 5 definition. We need not do LHL and RHL. Limit extending to c of f of x. Here c is less than 5. We will use less than 5 definition, which is minus of x minus 5. Directly we will substitute the limit value. Minus of c minus 5 is 5 minus c. And f of c is minus of c minus 5, which is 5 minus c, using x less than 5 definition. Limit extending to c of f of x equal to f of c. Therefore, f is continuous in the interval minus infinity to 5. Case 3. Now, we will check for all real values which are greater than 5. Let c belongs to 5 comma infinity, open interval. limit extending to c of f of x equal to limit extending to c of, here c is greater than 5. We will use greater than 5 definition, which is x minus 5. The answer is c minus 5. F of c, again we will be using greater than 5 definition, which is c minus 5. Limit extending to c of f of x and f of c are equal. Therefore, f is continuous in the open interval 5 to infinity. Therefore, f is continuous in R. Therefore, there is no point of discontinuity. Question 4. Prove that the function f of x equal to x raised to n is continuous at x is equal to n, where n is a positive integer. Limit extending to n of f of x is limit extending to n of x raised to n, which is n raised to n, where n is a positive integer, and f of n is also n raised to n. Limit extending to n of f of x and f of n are equal. Therefore, f is continuous at x equal to n, where n is a positive integer. Question number 5. Is the function f defined by f of x equal to x if x is less than or equal to 1, 5 if x is greater than 1, continuous at x equal to 0, at x equal to 1 and at x equal to 2. First one, let us check at x equal to 0. At x equal to 0, we are going to use less than 1 definition. Only one definition is there for 0. Therefore, we need not do LHL, RHL. Limit extending to 0 of f of x is limit extending to 0 of 0 is less than 1. We will use x less than or equal to 1 definition, which is x. It is a polynomial, direct substitution, the answer is 0. And f of 0, same definition, which is 0. Both are equal. Therefore, f is continuous at x is equal to 0. Now, let us check at x equal to 1. At x equal to 1, we have two definitions for less than or equal to 1 and greater than 1. We need to do LHL and RHL. LHL is equal to limit extending to 1 minus. For 1 minus, we need to use less than 1 definition, which is x. We will directly substitute the value, which is 1. RHL is equal to limit extending to 1 plus f of x. For 1 plus, we will use more than 1 definition. Greater than 1 definition is 5, which is a constant. The answer is 5. LHL and RHL are not equal. Therefore, f is discontinuous at x equal to 1. Now, we will check at x equal to 2. For x equal to 2, we will be using x greater than 1 definition. We have only one definition, so we need not do LHL and RHL for 2. Limit extending to 2 of f of x. 2 is greater than 1. For x greater than 1, the definition is 5. The answer is 5. And f of 2 is also 5. Limit extending to 2 of f of x and f of 2 are equal. Therefore, f is continuous at x equal to 2. Next question. Find all points of discontinuity of f where f is defined by, question number 6, f of x equal to 2x plus 3 if x is less than or equal to 2, 2x minus 3 if x is greater than 2. In this question, it is not mentioned at which point we have to check the continuity, and the definition has been split at 2. So, we will first check the continuity at 2 and then we will check for all real values less than 2 and for all real values more than 2. Case 1, we will check at x equals 2. LHL will be limit extending to 2 minus f of x, limit extending to 2 minus. For 2 minus, we will use less than or equal to 2 definition, which is 2x plus 3, which is a polynomial. Direct substitution of the limit value gives 4 plus 3, which is 7. RHL is equal to limit extending to 2 plus f of x. For 2 plus, we have to use greater than 2 definition. We get limit extending to 2 plus 2x minus 3. This is also a polynomial. Direct substitution of the limit value gives 4 minus 3, which is 1. LHL not equal to RHL. Therefore, f is not continuous at x equal to 2. Case 2. Now we will take C belonging to all real values less than 2, that is minus infinity to 2, open at 2. For less than 2, we have only one definition. We need not do LHL and RHL. Limit extending to C of f of x, where C is less than 2. Let us use less than 2 definition. Limit extending to C of 2x plus 3, which is a polynomial. Direct substitution gives 2c plus 3. And f of c is also 2c plus 3. Limit extending to c of f of x and f of c are equal. Therefore, f is continuous for all c belonging to minus infinity to 2. Let us do case 3. We will check for all real values which are more than 2. So, c belongs to 2 to infinity. Limit extending to c of f of x. In this case, c is greater than 2. So, we will use 2x minus 3 definition, which is a polynomial. Directly we can substitute the limit value. The answer is 2c minus 3, and f of c is also 2c minus 3. Limit extending to c of f of x and f of c are equal in this interval. Therefore, f is continuous for all c belonging to 2 to infinity. Therefore, x equal to 2 is the only point of discontinuity. Question 7. Find all points of discontinuity of f of x, which is absolute value of x plus 3, where x is less than or equal to minus 3, minus 2x for minus 3 less than x less than 3, 6x plus 2 for x greater than or equal to 3. In the first definition, x is less than or equal to minus 3. That means all x values are negative. So, for negative values, we know that absolute value of x should be replaced by minus x, because the definition of absolute value of x is x when x is greater than or equal to 0 minus x when x is less than 0. Here, x less than or equal to minus 3 will take all negative values. We will be using this definition. So, absolute value of x becomes minus x in this case, where x is less than or equal to minus 3. Other definitions are same. We have to check the continuity at all real values. The definition has been split at minus 3 and at 3. So, we will first check the continuity at minus 3 and at 3, and then we will check the continuity for all real values which are less than minus 3, and for all real values between minus 3 and 3, and for all real values which are more than 3. Case 1, we will check at x equals minus 3. At minus 3, we have two different definitions. For less than or equal to minus 3 and greater than minus 3, we need to do LHL, RHL. LHL is limit extending to minus 3 minus, that is approaching minus 3 from the left side of minus 3. We will be using less than or equal to minus 3 definition, which is minus x plus 3. It is a polynomial. Directly we can substitute the limit value. Minus of minus 3 becomes plus 3. The answer is 6. RHL is equal to limit extending to minus 3 plus f of x. Limit extending to minus 3 plus, we have to use greater than minus 3 definition, this definition, which is minus 2x. Polynomial, direct substitution of the limit value gives minus 2 times minus 3 plus 6. And f of minus 3. For f of minus 3, we have to use equal to minus 3 definition, which is minus x plus 3, minus of minus 3 plus 3, which is 6. LHL equal to RHL equal to f of minus 3. Therefore, f is continuous at minus 3. Case 2, we are going to check at x equal to 3. LHL is limit extending to 3 minus f of x. For 3 minus, we have to use less than 3 definition, which is the second one. Limit extending to 3 minus minus 2x. It is a polynomial. Directly we will substitute 3. Minus 2 times 3 is minus 6. Let us find RHL. Limit extending to 3 plus f of x. Limit extending to 3 plus. For 3 plus, we have to use greater than 3 definition, 6x plus 2. We will directly substitute 18 plus 2 is 20. Here LHL and RHL, they don't coincide. Therefore, f is discontinuous at x equal to 3. In case 1, we checked the continuity at minus 3, and in case 2 at x equal to 3. Now we will check for all real values which are less than minus 3. Case 3, let c belongs to minus infinity to minus 3. We need not do LHL, RHL for this case because we have only one definition, which is x less than or equal to minus 3 definition. Limit extending to c of f of x. Limit extending to c of f of x is minus x plus 3. By substituting the limit value, we get minus c plus 3, which is 3 minus c. And to find f of c, we use the same expression. The answer is 3 minus c. Limit extending to c of f of x and f of c are equal. Therefore, f is continuous in the open interval minus infinity to minus 3. Now, next case, we will check for the interval minus 3 to 3. Case 4, let c belongs to the open interval minus 3 comma 3. In this interval, we have only one definition. No need to do LHL, RHL. Limit extending to c of f of x is limit extending to c of, in this interval, f of x is minus 2x. By substituting the limit value, we get minus 2c, and f of c is also minus 2c. Both are equal. Therefore, f is continuous in the open interval minus 3 to 3. Now, last case is we are going to check in the interval 3 to infinity. Case 5, let c belongs to open interval 3 to infinity, limit extending to c of f of x. In this interval, f of x definition is 6x plus 2. We get 6c plus 2. F of c is also the same thing. limit extending to c of f of x is equal to f of c. Therefore, f is continuous in the open interval 3 to infinity. Therefore, f is discontinuous at x equal to 3. And this is the only point of discontinuity. Question 8. Find all points of discontinuity of f, where f of x is absolute value of x divided by x if x is not equal to 0, 0 if x is equal to 0. And this is Signum function. We know that absolute value of x becomes x when x is greater than 0 and minus x when x is less than 0. Therefore, absolute value of x divided by x becomes x by x, which is 1 for x greater than 0, and minus x divided by x, which is minus 1 for x less than 0. Therefore, Signum function definition can be written as 1 if x is greater than 0, 0 for x equal to 0, and minus 1 for x less than 0. Case 1, we will first check the continuity at x equal to 0. LHL is limit extending to 0 minus f of x. For 0 minus x less than 0 definition, which is minus 1, the answer is minus 1. RHL is limit extending to 0 plus f of x. For 0 plus x greater than 0 definition, which is 1, the answer is 1. LHL is not equal to RHL. Therefore, f is discontinuous at x equal to 0. Or we need not do RHL. F of 0 is 0, LHL is minus 1. So, LHL not equal to f of 0 also we can say. Therefore, f is discontinuous at x equal to 0. Case 2, we will check for all real values belonging to the open interval minus infinity to 0. Limit extending to c of f of x. In this interval, the values are all negative. Limit extending to c of c is negative. In this case, we will use x less than 0 definition, which is minus 1. And f of c, as c is negative, again f of c is minus 1. Limit extending to c of f of x and f of c are equal. Therefore, f is continuous in the open interval minus infinity to 0. Case 3. Let c belongs to the open interval 0 to infinity. Limit extending to c of f of x. In this interval, the values are all positive. We will use x greater than 0 definition, which is 1. The answer is 1. And f of c, c here is positive. Therefore, the answer is 1. Limit extending to c of f of x and f of c are equal. Therefore, f is continuous in the open interval 0 to infinity. The only point of discontinuity is x equal to 0. Therefore, f is discontinuous at x equal to 0. Question 9. Find all points of discontinuity of f, where f is defined by f of x equal to x divided by absolute value of x if x is less than 0, minus 1 if x is greater than or equal to 0. For x less than 0, we know that absolute value of x is minus x. We will write it as minus x. It becomes minus 1 for x less than 0 and minus 1 when x is greater than or equal to 0. Whereas in the previous question, we had the function absolute value of x divided by x for x not equal to 0. And this function takes different values for positive x and negative x. Whereas here, x divided by absolute value of x is only for negative values of x. We will first check the continuity at 0 and then for all real values less than 0 and for all real values greater than 0. Case 1, at x equal to 0. LHL is limit extending to 0 minus f of x. Limit extending to 0 minus, we have to use less than 0 definition, which is minus 1. The answer is minus 1. RHL is equal to limit extending to 0 plus f of x. Limit extending to 0 plus, we will use x greater than or equal to 0 definition, that is also minus 1. The answer is minus 1. F of 0, x equal to 0 definition is minus 1. LHL equal to RHL equal to f of 0. Therefore, f is continuous at x equal to 0. Case 2. We will check for the interval minus infinity to 0. Let C belongs to the open interval minus infinity to 0. In this interval, all C values are negative. Limit extending to C of f of x equal to limit extending to C of, as C is negative, we will use x less than 0 definition, which is minus 1. And f of C, again the same definition, minus 1. Limit extending to C of f of x and f of C are equal. Therefore, f is continuous in the open interval minus infinity to 0. Case 3. Let C belongs to the open interval 0 to infinity. Limit extending to C of f of x. In this interval, C values are all positive. We will be using x greater than or equal to 0 definition, which is minus 1. The answer is minus 1. F of C equal to, C is positive in this case. For x greater than or equal to 0, the definition is minus 1. Limit extending to C of f of x and f of C are equal. Therefore, f is continuous in the open interval 0 to infinity. Therefore, f is continuous in R. There is no point of discontinuity. Tenth question. Find all points of discontinuity of f of x, where f of x is x plus 1 if x is greater than or equal to 1, x square plus 1 if x is less than 1. We will check the continuity at 1 first, and then for all real values which are less than 1, and we will check for all real values which are more than 1. Case 1, at x equal to 1. At x equal to 1, we have to do LHL, RHL because we have greater than 1 and less than 1 definitions. LHL is limit extending to 1 minus f of x. Limit extending to 1 minus. For 1 minus, we will use x less than 1 definition, which is x square plus 1, and it is a polynomial. Directly we will substitute the limit value 1 plus 1, 2. RHL is limit extending to 1 plus f of x. For 1 plus, we will use greater than or equal to 1 definition. Limit extending to 1 plus x plus 1, which is a polynomial. Directly we will substitute the limit value. And f of 1, use equal to 1 definition, 1 plus 1, this is also 2. LHL equal to RHL equal to f of 1. Therefore, f is continuous at x equal to 1. Now, case 2. We will check for all real values which are less than 1, that is minus infinity to 1. In this interval, we have only one definition, less than 1 definition. So, need not do LHL and RHL. Limit extending to C of f of x. Limit extending to C of f of x is x square plus 1 in this case. Directly we can substitute the limit value, and f of c, we use the same definition, c square plus 1. Limit extending to c of f of x and f of c are equal. Therefore, f is continuous in the interval minus infinity to 1. Case 3. We will check for all real values which are more than 1, 1 to infinity. 1 to infinity we are going to use greater than 1 definition. Limit extending to c of f of x equal to limit extending to c of greater than or equal to 1 definition is x plus 1. It is a polynomial. Directly we will substitute the limit value, and f of c is also c plus 1. Limit extending to c of f of x and f of c are equal. Therefore, f is continuous in the open interval 1 to infinity. Therefore, there is no point of discontinuity. Question 11. Find all points of discontinuity of f where f of x is x cube minus 3 if x is less than or equal to 2, x square plus 1 if x is greater than 2. Here the definition has been split at 2. We will first check the continuity at 2, and then we will check for all real values less than 2, and then for all real values greater than 2. Case 1. At x equal to 2. We need to do LHL RHL because we have less than 2 greater than 2 definitions. LHL is equal to limit extending to 2 minus f of x. For 2 minus we will use x less than or equal to 2 definition. Limit extending to 2 minus f of x is x cube minus 3, which is a polynomial. Directly we will substitute the limit value. 2 cube minus 3, 8 minus 3, which is 5. RHL is limit extending to 2 plus f of x. For 2 plus we use greater than 2 definition. We get limit extending to 2 plus f of x is x square plus 1. This is also a polynomial. Directly we will substitute the limit value. 4 plus 1 is 5. And f of 2, we will use x equal to 2 definition, which is x cube minus 3, 2 cube minus 3, 8 minus 3 is 5. LHL equal to RHL equal to f of 2. Therefore, f is continuous at x equal to 2. Case 2. Now we will check for all real values which are less than 2. Let C belongs to the interval minus infinity to 2. We have only one definition for all real values which are less than 2. We need not do LHL and RHL. We will take limit extending to c of f of x. In this case, c is less than 2. We will use less than 2 definition, which is x cube minus 3. By substituting the limit value, we get c cube minus 3. And f of c, using the same definition, we get c cube minus 3. Limit extending to c of f of x and f of c are equal. Therefore, f is continuous in the open interval minus infinity to 2. Case 3. Now we will check for the interval 2 to infinity. So we will take c belonging to the open interval 2 to infinity. Limit extending to c of f of x. For greater than 2, the definition is x square plus 1, which is a polynomial. Directly we will substitute the limit value. We get c square plus 1. And f of c, again c is greater than 2. Using the same definition, we get c square plus 1. Limit extending to c of f of x and f of c are equal. Therefore, f is continuous in the open interval 2 to infinity. Therefore, there is no point of discontinuity for f. Question 12. Find all points of discontinuity of f, and f of x is x raised to 10 minus 1 if x is less than or equal to 1, and x square if x is greater than 1. We will first check the continuity at x equal to 1, and then for all real values less than 1 and for all real values greater than 1. Case 1, at x equal to 1. We need to do LHL RHL for 1. LHL is limit x tending to 1 minus f of x. For 1 minus, we will use less than 1 definition, which is x raised to 10 minus 1. It is a polynomial. Directly we will substitute the limit value. 1 raised to 10 minus 1. 1 minus 1 is 0. RHL is limit x tending to 1 plus f of x. For 1 plus, we use greater than 1 definition, which is x square. This is also a polynomial. Directly we will substitute the limit value. And in this case, LHL and RHL don't coincide. Therefore, f is discontinuous at x equal to 1. Case 2. Now we will check for all real values which are less than 1. We will take c belonging to the open interval minus infinity to 1. Limit x tending to c of f of x. Limit x tending to c of x raised to 10 minus 1. Substituting the limit value, we get c raised to 10 minus 1. And f of c is also the same, c power 10 minus 1. Limit x tending to c of f of x and f of c are equal. Therefore, f is continuous in the open interval minus infinity to 1. Case 3. Now we will check for the next interval 1 to infinity. Limit x tending to c of f of x. Here c values are greater than 1. We will use greater than 1 definition, which is x square. Substituting the limit value, we get c square. And f of c, using the same function, we get c square. Limit x tending to c of f of x and f of c are equal. Therefore, f is continuous in the open interval 1 to infinity. Therefore, f is discontinuous at 1 point, x equal to 1. Question 13. Is the function defined by f of x equal to x plus 5 if x less than or equal to 1, x minus 5 if x greater than 1, a continuous function? We will check the continuity at x is equal to 1 first. LHL is limit x tending to 1 minus f of x. Limit x tending to 1 minus. For 1 minus, we will use x less than or equal to 1 definition, which is x plus 5. By substituting the limit value, we get 1 plus 5, which is 6. RHL is equal to limit x tending to 1 plus f of x. We will use greater than 1 definition, which is x minus 5. By substituting the limit value, we get 1 minus 5, which is minus 4. LHL and RHL are not equal. Therefore, f is discontinuous at x is equal to 1. Case 2. We will check for all real values which are less than 1. So, c belongs to minus infinity to 1. Limit x tending to c of f of x. Limit x tending to c of, in this interval, c values are less than 1. We will use x plus 5. The answer is c plus 5. and f of c is also c plus 5 using the same function x plus 5. Limit extending to c of f of x and f of c are equal. Therefore, f is continuous in the open interval minus infinity to 1. Case 3. Let c belongs to 1 to infinity. Limit extending to c of f of x is equal to limit extending to c of, here c values are all more than 1. We will use greater than 1 definition, which is x minus 5. By substituting the limit value, we get c minus 5. F of c is also c minus 5. Limit extending to c of f of x is equal to f of c. Therefore, f is continuous in the open interval 1 to infinity. So, the only point of discontinuity is x is equal to 1. Therefore, f is not continuous at x equal to 1.